Okay, so welcome again to today's talk, and today we shall be discussing matrices and transformations. I think this is a topic is covered in Form 4, but with some previous exposure, I think in Form 2 as well, if I'm not wrong. Yeah. So we may not be able to go very deep into any difficult examples or demanding examples. I think there's some noise. Let me see if I can. Yeah, okay. Yeah. So we may not be able to go into very serious examples or demanding examples. We'll just have an overview of matrices and transformations. Hopefully, we'll be able to finish all these topics. We'll have some introduction. We see how to represent transformations as matrices, and then how to find the matrix of a given transformation. And we'll also learn how to work with successive transformations. So these 4 topics are what we want to cover today. Again, we shall just have an overview. So we start that transformations will simply be, they will simply change the properties of an object, and that may be the position, the size, or the shape, and those are the ones we'll consider. Or it can also be more than one of these or all of them. A given transformation can do all that. So we shall also be a little restricted on transformations that can be represented as matrices. There are some that cannot be represented as matrices, but the ones we are considering as matrices will be those that I don't know how to say it without talking about linear algebra. They're what we would call linear transformations, and the ones that leave the origin fixed. They don't move the origin. We'll see that does not explain the full story, but partly that is what the kind of transformations we shall be looking at. So we look at rotations, reflections, and enlargement. And this transformation will work on some object, and the final image after the transformation will be called the image. I think that may not be entirely new. So we consider rotations. So a rotation, to perform a rotation, you need a center of rotation, and then the object is rotated through a given angle. So you must have an angle of rotation and the center of rotation. We shall illustrate this shortly. If you rotate in the anti-clockwise direction, we say that is positive. If you move in the clockwise direction, we say that's a negative rotation. We go through a negative angle. So rotations are some kind of rigid motions. They do not change the size of the object. They only change the position. So the object is exactly the same size as it was. The image and the object are they're actually congruent. They're the same size. So here is an illustration for the rotation. So we have our object, this triangle labeled P, Q, and R. Just give me a minute. So we have the triangle labeled P, Q, and R. And after the transformation, the 90 degrees rotation, the image is this green triangle, P prime, Q prime, and R prime. So you can, if you draw the center of rotation here is the origin. So if you draw a line from the center to the point P, and a second line from the center to the image of P prime, now the angle between those two lines should actually be the angle of rotation. which is 90 degrees. Now you notice when we are considering these transformations, for instance, an object like this, we only focus on the vertices, or if you like to call them corners. These vertices are the only ones we focus on. So we don't worry too much at what is between the vertices. Once we find the position, the new position of the vertices, we'll be able to determine the rest of the object by just joining the lines between the vertices, the images of the vertices. So the only thing you need to worry about are the vertices. Likely because these transformations that we look at usually will send a line to a line. So let's see if we'll try to see what this looks like in GeoGebra and how it is done, the rotation. So it's loading. Here we go. So I hope you can see the screen. I'll just start from here. So we're going to illustrate the rotation using GeoGebra. So the first thing we do is to draw the object to be transformed. You can see my screen. So we just use a triangle, but it doesn't have to be a triangle. So you can see the vertices of a triangle are shown on the side here, on this bar at the side. So now we need to transform it. So we set up the center of rotation here. It's this point D, the origin. Now to rotate it, you select it, the object that you want to rotate, select the center of rotation and determine the angle of rotation. And then you press and you have your image. It's that simple. So that's the rotation. So we can illustrate this if you pick the line and if you draw a line from the origin or the center of rotation to the point A and another line to the image of A, then the angle here will be 90 degrees. That's precisely the angle of rotation. And this should be true for any other point and its image. So if you draw another line to C and another line to the image of C from the center of rotation, the angle will be 90 degrees. So I think I can, so that's the last one from B and B prime. So in all cases, the angle should be 90 degrees. So you can also change the colors of the object so that the image has a different color from the object if you want to distinguish the two. So the green is the image and the object is this brown triangle. So I will move back to the presentation. So the next we'll look at is enlargement. Enlargement, this simply changes the size of an object, but preserves all the angles and ratios of a corresponding side. So what you end up with is a similar object. The image is similar to the original object. And how big the enlargement will be is determined by the center. Again, you will also need the center for you to perform this. So the two things that you will need is the center and the linear scale factor or the enlargement factor to be able to perform this operation. So once you determine the center and the scale factor, then you're able to perform the operation. Again, we shall do this on the GeoGebra shortly, but this is an example of the enlargement. So we have this rectangle ABCD. The enlargement center is the origin, which is just here, and the image is A prime, B prime, C prime, and D prime. If you draw a line from the origin or the center of enlargement to the point D and all the way to the image D, it will be a straight line. And the ratio of this distance from the origin to D to the distance from the origin to D prime should be the scale factor itself, 2. So the distance from the origin or the center of enlargement to D prime should be twice the distance from the origin to D, because the scale factor is 2. And the line from the center will go through both points. It happens for all the other points. You can see the same is true for A and A prime, C and C prime, and so on. So let's see what it looks like in GeoGebra. So you can see the screen. This is the one I'm looking for. It's moving too fast. There, let me align it properly. So this enlargement, it has already drawn the rectangle. So the center is the origin here. You can pick the transformation tools and pick the dilate object. So the enlargement here, you'll pick the menu option that says dilate object. Select the object, press on the center of enlargement, and put the scale factor. And then you have the image. The image is reproduced. You can change the color of the image so that we can distinguish it from the object. And there we have it. So you can measure the distance on GeoGebra just to check what happens if you measure from A to B, because the scale factor is 2. The corresponding side should be twice this on the image. So we need to measure A prime to B prime, and you will see that it will be equal to twice this, and it's actually 8 units. So the scale factor is 2. 8/4 will give you 2. So the same is true for all the other sides. They will retain the ratios. You can see also the angles are retained. The only thing that changes is the size. So we end up with an object that is similar. The image is similar to the original object. I think I will, there may not be much more to show here. So we'll just go back to the presentation. So the third one is a reflection, and this one simply flips an object over a given line of reflection. So to perform this one, you need a mirror line, sort of. So the line becomes like a mirror. So you will always need a mirror line. And each point of the object and the corresponding point on the image will be exactly the same distance from the mirror line. So I've said this already, we need a line of reflection for us to define reflection. So here's an example. Our reflection is the y-axis. The line of reflection is the y-axis. Our original object is on the right-hand side, here, A, B, C, D. And after reflection, we can see it's on this end. And you can see the distance, say, from A to this reflection line is 2 units. And it's the same distance from the image A prime to that line. So let's see how it works in, I think this is the last video we'll watch. The rest now will move a little faster. So we have the object. Now we are set up the line of reflection. The line of reflection, the first one we shall look at is the y-axis. And then to do the reflection, simply pick the transformation tools, reflect about the line. Then you select the object and click on the line, and you get the image. The reflection does not change the size. We can change the color of the image. That way we can distinguish it from the. So now you can see what happens if you draw a line from A to its image A prime. It will make an angle of 90 degrees with the line of reflection. And that will be true for any other line joining a point and its image. The line joining the 2 points will always make an angle. I mean, it will make there will be the same distance. The 2 points will be the same distance from the line of reflection. So here, the second one is just reflecting along the x-axis. Again, we change the color. So now this red one is a reflection of the original object, but now we are doing it along the x-axis. So this is the image. We should be doing one more. So we do the reflection along the line y is equal to x. So we first draw the line. Then we perform the reflection. We need to click on the menu tools, go to transformation tools, reflect object about line, pick the object, and then click on the line, and you can see the image. So this last one is a reflection of the original rectangle. Along the line y is equal to x. So this is the line y is equal to x, and that's the image of this reflected along that line. So I think that's we can go back to the slides now. So well, the aim finally was to be able to write transformations as matrices. So if you observe the all through for the reflection and the enlargement, we considered the origin as the center for both cases. And when we considered lines, we only considered lines that are passing through the origin, because those are the ones that we'll be able to represent as matrices. So we'll illustrate this using an example. So we'll pick an example of this, a triangle with these vertices. 1, 3 is a point P, 4, 3 is a point Q, and 3, 5 is a point R. Now it's possible to represent this as position vectors. And then we have a matrix here. We want to see what is the effect of this matrix on these position vectors. So once we have the effect of this matrix on these position vectors, we can try to figure out what transformation it represents. So I don't know if everyone has had a good look at this. So this is what we want to solve. So what we're going to do is simply multiply each of these vectors by this, pre-multiply by this matrix, and the resulting position vector will be the position vector of the image. So we do that for each of the vectors. So the point 1, 3 is sent to the point negative 1, 3. The point 4, 3 is sent to the point negative 4, 3. And the point 3, 5 is sent to the point negative 3, 5. So for the students, I think I assumed any students, if attending, will have some knowledge of matrix multiplication. I don't think Is there anyone? Can you hear me?
Yes, Doctor, we can hear you.
Hello?
Hello.
Oh, okay. So there's probably no student who was a problem, I think. So by pre-multiplying all the vertices as position vectors, we get the corresponding vertices for the image. And we label the three new points P prime, Q prime, and R prime, and they still give us a triangle. Now, if you look at I did not draw the diagram, but this is clearly a reflection along the y-axis. Maybe we can see that by going back to the. So what happens when you reflect along the y-axis? You move horizontally, right? So the y-coordinate does not change, but the x-coordinate will change sign. It's the same with all the others. The y-coordinate does not change, but the x-coordinate will change sign because it will be the same distance from the y-axis as the original point. So since you're moving horizontally, the only thing that will happen is that changes sign. So this is actually the reflection along the y-axis, and we can say that this matrix represents that reflection along the y-axis. So this is an example to show us that a transformation can be represented as a matrix. We shall see something more interesting later, and figure out how to determine a matrix of a non-transformation. So this is a diagram actually. I thought I hadn't drawn the diagram. So this is the reflection. You see this is the original triangle, and it is sent to this image. And it's the matrix is up here. And the line of reflection is the y-axis. So let's see. So anytime you're given a transformation, you may want to figure out if you can represent it with a matrix. So if you start from the matrix, we can try to identify the transformation by applying it to some object, and we do this using an example. So for instance, suppose we're given these matrices, we wish to figure out what transformations they represent. So we would have to create some object, apply these matrices to the object, and see what effect it has on the object, and see if we can, from that, we can determine the transformation itself. So let's check. This is the process I've just described. So we shall pick the triangle to be the one with the points P, Q, R as the vertices. So that is 2, 1, 4, 1, and 4, 3. Then we apply in turn the matrices to each of these points. Now, in the previous example, we multiplied each vector one by one, but there's an easier way. You can write out all these points as vectors in a matrix. So you'll end up with a 2 by 3 matrix, and then you multiply it with your transformation matrix. So that's what we have done here for this. The first one, we put all the 3 points for the object, and then we multiply by the transformation matrix, and we get the points for the images on this side. So this illustrates the assignment. 2, 1 is assigned to -1, 2. 4, 1 is assigned to -1, 4, and so on. So if we plot the original triangle and the image, we observe that this is actually a 90-degree rotation. If you draw a line from here to P, the origin to P, and the origin to its image, the angle is 90 degrees. So it's a 90-degree rotation about the origin. The second example, we do the same thing. So instead of multiplying each vector one by one, you just put all of them in order in the matrix, and their images will appear in the same order. So 2, 1 under this transformation. Again, I'm assuming the matrix multiplication is already done. It would be a good idea to simply work it out on your own, just in case I made an error in the calculations, but I try to check them. I hope they are error-free. So 4, 1 will be sent to -4, -1. 4, 3 will be sent to -4, -3. So again, when we plot this, we see that it's just a rotation, about 90 degrees. Sorry, 180 degrees. I think I was still stuck in the previous example. So this is a matrix for the rotation about 180 degrees. Again, the center is the origin. The center of rotation is the origin. So the last example was this matrix 2, 2, 2, 0, 0, 2. So when you apply that to our triangle, this is what we get as the image. 2, 1 is sent to 4, 2, 4, 1 is sent to 8, 2, and 4, 3 is sent to 8, 6. And if we look at the diagram that follows, we'll observe that it's actually an enlargement centered at the origin and scale factor 2. So we shall look at this next time. We shall look at this in more detail and try to understand what happens when we have the general form of some of these transformations. But today we shall just do an overview. So I will not go deep into what happens, what kind of matrix should be an enlargement, and so on. We can do that next time when we're working with for the second talk. So now, the previous examples we have done is where we have a matrix and we try to determine what transformation it represents. So the next case, we want to look at a situation where you have a transformation described and you want to figure out what, how you want to determine the matrix that represents the transformation. So the one way to do this is to, because since you're given a transformation, most likely you have an object on which it has been applied. You assume, since we're working with 2 by 2 matrices, you pick an arbitrary 2 by 2 matrix and multiply it by the position vector of the object to get the position, and equate rather to the position vectors of the image. Once you equate them, then you'll end up with some simultaneous equations which you can solve to find the entries of your matrix. So in this case, we must have the object and the image for this to work. If you have both, you need both the object and the image of the transformation. Once you have that, then you can work backwards to obtain the matrix. So here is an example. We have a triangle PQR, which has the vertices P, Q, and R. That's 4, 1, 7, 1, and 7, 5. And it's rotated to an angle of 90 degrees. So we already know the transformation. And now we also given the image. So what we need to do is to find the matrix of this transformation. So the strategy will be to pre-multiply this by some arbitrary matrices where we put in variables and then determine the values of those variables by equating the product of that matrix and the matrix made up of these vertices of the object and equated to the matrix made up of the vertices of the image. So I will move to the, so we set up the matrix. We don't know what the matrix will be, so we put in some variables X, Y, Z, and T, and we'll try to determine what they are. So the position vectors for the object were 4, 1, 7, 1, and 7, 5. We set up this matrix here, multiplied by this arbitrary 2 by 2 matrix that we are trying to determine. And these are, the answer should be this because this is the image. So after multiplying this out, this is what you have. So what you need to do is to compare the slots in the corresponding positions on both ends. So for instance, here we have 4x plus y will be equal to -1. That gives us one equation in x and y. 7x plus y will be equal to -1 as well, I think. Did I write this correctly? -1, 4, -1, 7. I think so. This one has not moved. No, it's fine. I wrote it correctly. So we have two simultaneous equations in x and y, and we can do the same for z and t. And when we solve those simultaneous equations, we get the values for this matrix. These are non-matrix right now. So are there any questions so far, or?
Hello, Dr.
Yes.
I'm following you, and thank you for this lecture.
Yes.
I have this concern. I can't understand that there is no t in the upper line, the 4x plus y, 7x plus y, and 7x plus 5y.
Yes, there should be no t. How you do the multiplication is as follows.
I understand. We use t at the lower line.
Yes.
The phone I'm using did not show the t, so I thought it was hidden somewhere.
Oh, okay. So I think we're on the same page now. So we can proceed. So this is the setup we end up with. You have this, we have these two sets of simultaneous equations. Now you actually, you have an oversupply of equations here. So you can pick any two here to use. For instance, I could use 4x plus y is equal to -1, and 7x plus 5y is equal to -5. That will also work. Or I use 7x plus y is equal to -1, and 7x plus 5y is equal to -5. Any of those should give me the correct answer if the transformation does exist. So we just use the first two in both cases, where for x and y, and also for z and t. So this is a simultaneous equation in x and y, and after we solve it, we get x is 0 and y is -1. Again, we have another pair of simultaneous equations in z and t. And after solving them, we get z is equal to 1 and t is equal to 0. Now, I did not go into the details of the solution. I suppose there's no one who has a problem solving this. There should be, if there are any students who have attended and they have questions on this, feel free to ask. So we have found the values of x, y, z, and t. We can simply put them back into our matrix, and we have the matrix of transformation. So this is a matrix for, I think it was what, rotation about 90 degrees, about the origin, through 90 degrees about the origin. So initially we didn't know what the matrix was. We just had the object and the image. And now we have the matrix that represents the same transformation of 90 degrees. So we have been able to, from the transformation where we have the object and the image, we're able to work our way through and obtain the matrix that represents the transformation. Now, this is a rather difficult way of solving the problem. There are simpler ways, which there's one other way we shall consider in this next section. So we are going to look at an easier way to find the matrix. So to understand how it works, we shall use the unit square. So you simply pick a matrix and consider its action on the unit square. So if you pick these 2 points on the unit square, the point 1, 0 and 0, 1, and use them as objects under some transformation matrix, the image will simply be the columns of the matrix. So this is where we get the idea. The images of the points I and J are simply, in that order, the columns of the matrix of the transformation. So if you're given any transformation and you try to find the image of I, which is 1, 0, and J, which is 0, 1, then the two images will form the columns of your matrix of transformation. Let's illustrate this with an example, what it becomes. So that is basically our strategy. Find the images of 1, 0, and 0, 1, and they give you the columns of a matrix of transformation. So if you can see this here, if you multiply, given any matrix of transformation, if you multiply it with this identity matrix, 1, 0, 0, 1, you end up with the columns of the matrix. So the images of 1, 0, and 0, 1 simply gives you the matrix. So that's where we get the trick. Simply find the images of I and J, and you have your matrix. So we'll look at an example. This one is simple. So we have these two matrices, and we want to see their impact on the points I and J on the unit square. And when the first one simply does not change the matrix. So it still gives you back your matrix of transformation. The same happens with the second one. If you multiply, because basically you're multiplying this with an identity matrix, so it doesn't change the matrix. So that is our strategy now. Anytime we want to find the matrix of transformation, we simply find the images of the points 1, 0, and 0, 1. And the result that we get will be the matrix of a transformation. You can see the matrix does not change at all. So by just applying the transformation to the unit square, we should be able to describe it. Let's look at an example. So we apply this matrix to the unit square in our example. And this is what we get. And the point 1, 0 is sent to the point 3, 0 under this transformation. 0, 1 is sent to 0, 3, and 1, 1, which is the other point on the unit square, is sent to 3, 3. It would be this ij and p. One j is a 0.01. So you can see this is an enlargement centered at the origin, and the scale factor is 3. So by just applying it to the unit square, you can quickly see what it represents. So in this second one, we want to find the matrix of a negative quarter turn about the origin. So negative simply means you are turning clockwise, I think. So we apply, I think if you are working this out, you'd have to draw it on a graph paper, or at least squared paper, to be able to see it work properly. So under this transformation, the negative quarter turn, 1, 0 will be sent to 0, negative 1, and 0, 1 will be sent to 1, 0. So these two images of 1, 0 and 0, 1, these two images are what form the columns of our matrix of transformation. So the matrix of a negative quarter turn will be 0, -1, 1, 0. I think there's a diagram for this as well. So the original, this brown image is original. Then you turn negative quarter turn, which is 90 degrees. And you get this green as the image. The green one now becomes your image. And now you see J here, which is 0, 0, 1 is mapped onto 1, 0. And then I here, which was 1, 0, is mapped onto 0, -1. So we only need the images of those two to get the matrix of transformation. We don't need the image of this other vertex to get the matrix of the transformation. So here we have a reflection along the line y plus x is equal to 0. So again, remember we are focusing on lines of reflection that pass through the origin only. I think the next talk we can work on some more interesting examples. So remember we are getting the reflection on the line y plus x is equal to 0. We want to find the matrix representing this reflection. So again, when we shall look at the diagram shortly, but under this transformation, the image of 1, 0 will be 0, -1. The image of 0, 1 will be -1, 0. And we pick these two to form the columns of our matrix of transformation. The images of 1, 0 and 0, 1 in that order will form the matrix. The columns will form the matrix of the transformation. So here is the reflection itself. A line, this is a line y plus x is equal to 0. So if you pick I, the point I is sent to I prime under this reflection. So if you draw, you need to draw a line perpendicular to the reflection line and measure the same distance from the reflection line to the other opposite side to get the image. But this is done in GeoGebra, so it's in GeoGebra you don't need the line. But you see this I is sent to this point 1, 0 is sent to the point 0, -1, and the point 0, 1 is sent to the point -1, 0, and that gives you the matrix. I think the matrix was here, 0, -1 and -1, 0. So this is the matrix that represents a negative quarter turn centered at the origin. No, sorry, a reflection along. I'm still stuck again at the last example. It's a it represents the reflection. What? Something is not right. Yeah, represents this reflection. I was moving the slides backwards, so now I'm moving in the right direction. It represents the reflection along the line y plus x is equal to 0. I hope that makes sense. So, so the last thing we'll look at is successive transformation. There's more we can look at, but I don't think under the circumstances we are constrained by time. So in the next talk, we shall cover, we will solve a few more examples that are a little more interesting than the ones we have. Today was just an overview. Now, S and T, if you have two transformations and we call them S and T, then it's possible to successively apply them to an object. And they don't have to be two different transformations. You can also keep applying the same one repeatedly. So here we work with these transformations whose matrices are given by S and T. and see what happens when we have successive transformation. So the first case we shall work on is we apply T followed by S. So the first transformation that acts will be T, and the second one will be S. So, and we apply this to this triangle PQR with the vertices 1, 1, 1, 3, and 3, 5. And then after that, we apply S. So T is here. T will be the first one to act, followed by S. So the matrix T is, let's just confirm, T is this matrix 2, 0, 0, 2. So it's the first one to act, and these are our vertices. When we multiply this matrix by our position vectors for the vertices, we end up with this as the image. So this becomes our intermediate image. It's not our final image. We want T to act on the original object, and then the second transformation S will act on this intermediate image. Okay, so now we apply S. If you apply S to the image, remember the image was this 2, 2, 2, 6, and 6, 10. So we apply the matrix S to the image, we pre-multiply, and this is what we get as our final image. So this was just the intermediate image where T sent us, then S will send us to the final image. So this is the so the original triangle is this small one. This, I hope you can see this PQR, the brown one here. So after T acts, this is what you get. The green triangle is your intermediate image. Then S will act on this intermediate image, and we get the final image at the bottom. So now we have two successive transformations. We started with T followed by S. The order in which you do this matters. So it's important that you observe the order. Now, also you will notice that, we shall get to that later. There's a point I wanted to mention, but we'll get to that later. So this just shows how the transformation went. We started with T, which sent 1, 1 to 2, 2, and then applied S to this. It sends 2, 2 to 2, negative 2 as your final image. So these last three vectors are the image of the successive transformations. Oh, there's some noise. Let's see if I can mute. Gushu has a question, or I can see a hand is raised. Gushu. I can't hear you. I don't know, Karen, for some reason it's not clear. You're saying?
But we start by multiplying by T.
Yes.
Multiply by S.
You're asking if we should start with T or?
Yes. Why?
Let me go back to the and choose any order. The order you choose is up to you, but once you fix the order, if you choose to start with T, you will multiply with the matrix that represents T first to get the intermediate image, and then if your second transformation will be S, then you multiply the intermediate image with your matrix that represents S. It is basically, there's no reason why you must start with one, but you have to fix the order. Once you fix the order, the first one you choose to start with is the first one you multiply with. Then the second one will be the second one to be multiplied. I don't know if that answers your question.
Yes.
Okay. So we will still see the reversed order. So now here we have another pair of transformations. We have U and T. So U is this matrix 0, -1, 1, 0. You can try to figure out what this matrix represents. For now, we don't bother too much with that. So T is a transformation with this matrix, and U is a transformation with this matrix up here. And we are going to let the two act successively on this triangle PQR with the vertices 1, 2, 2, 2, and 2, 4. So the successive transformation that we're going to consider will first U followed by T, and the second will be T followed by U. So U followed by T will be worked out as this. The matrix U will act on the original object to give us our intermediate image. And then T will act on the intermediate to give us our final image. I don't know if I need to go through the calculations. It's not necessary. It's something you can double check just to be sure if I wrote them correctly. So basically now this illustrates the sequence of transformation. U acted first. I think it was U followed by T. Yes, we started with U followed by T. Now you can also see that in the diagram. The original object is this. So U acts first to give us this intermediate image, and T gives us this as a final image. So that's the order U followed by T. What if we work it out backwards? If we start with T followed by U, then we'll multiply this by T first to get the intermediate, then followed by U to get the final image. So if you look at the diagram, you will see that again. So the original one is this PQR. Then we have the intermediate one, which is this one down here, and then the final image. I didn't change the colors. Maybe I should have, but this P prime, Q prime, and R prime is the intermediate. Then Q double prime, P double prime, and R double prime will be the final image. That triangle, P double prime, Q double prime, and final vertex is R double prime. So you can see clearly that the order, the final image under this order is different, the order of this operation. When you have T followed by U, that's what you get. When you have U followed by T, this is what you get. So the order of transformation is different. Makes a difference. So now when you have any two successive transformations, instead of doing the multiplication twice, it's possible to find just one matrix that represents the transformation, but you have to be careful with the order. So if you have two transformations, say S and T, with which are represented by two matrices, say matrix A and B. So A represents S and B represents T. So if you have the okay, so if we apply T first, if T is the first one to act, followed by S, then we'll denote this by ST. The reason for this is that T will be the first one to act. So it will be the first one to act on the vector. After it acts on the vector, it gives you the intermediate on which S acts. But if so, the matrix that now will present this transformation ST will be AB. So B represents T, and it will be the first one to act, and S, A represents S, and it will be the second one to act. So this order is T followed by S. So the first one, when you're doing the matrix multiplication, the first one, the matrix that represents the first transformation will be last in the order, and the matrix that represents the second transformation will be first. So the order is reversed. But I think that makes sense. Any questions? So this idea can be extended to 3 or more transformations. And maybe we shall look at such examples next time. Today we'll focus on this example of 2 successive transformations only. So so here is an example. If you have U and T as your transformations, we want to find one matrix that represents each of the following successive transformations. So U followed by T, and then T followed by U. So we start with the first one, U followed by T. Remember, U is this matrix, and T is represented by this matrix. So U followed by T. So U followed by T will be written as TU. So we start from the right going to the left. U is the first one to act. T will be the second one to act. So the matrices are multiplied in that order. So the matrix for U will be on the right, and the matrix for T will be on the left. And when you multiply them out, you get one matrix. So this one matrix now represents the successive transformation. And if you have any objects that you want to transform, then instead of multiplying twice in succession, you simply use this one matrix to do the transformation. So the same happens to the next one. Here the order now is reversed, and we also get a new matrix. So again, this shows clearly why the order is important. You see, if you start from U and then you follow by T, this is a matrix that represents a successive transformation. But if you start from T, oh, this is repeated again. I think this second one is a mistake. Should be T followed by U. So that should be UT. The second, this sentence, I think, is wrong. Let's just check that the matrices also have been ordered correctly. Yeah, I think matrices are fine. So there's a mistake at the bottom here. It should be T followed by U. So that T acts first, followed by U. So when you multiply these two matrices in that order, you get one matrix that represents a transformation, which successive transformation, U followed by, T followed by U. So this here, this one should be UT. I think maybe I can correct that. I think this one should be T followed by, and this one should be U. So that means this one should be in the reverse order as well, because we move from the right towards the left. So T followed by U. And this is the matrix that represents the successive transformation. So instead of doing a double multiplication, for the successive transformation, you just need to use one, and you skip the intermediate image. You go to the final image. So I think that's all for today. Next time we shall do some more interesting examples. Like I said, today was just an overview, and maybe I try to put too much in one talk, but was a start. Are there any questions? You can hear me? Hello?
Yeah, we can hear you.
Okay.
Yeah,
Hakuna
we can
maswali?
hear you.
So, okay, thank you very much for joining us today. I think we shall meet again in 2 weeks' time. And we will cover now a little more interesting examples and further transformations also. And I think will be the last talk on transformations. So maybe after that we Olympiad maths training, after we cover this topic on transformations. We shall do some more demanding examples. Oh, there are some comments. Oh, okay. Okay. So any questions? Any comments? The floor is open.